Morning, everybody. My name is Thomas Motyka, and I am here today with my thesis partner, Eli Murray. We are here to present our thesis titled Webb's Open Circuit Wind Tunnel, Final Setup and Validation. We would like to thank our principal advisor, Professor Royce, for his guidance in the completion of our thesis, and we'd like to thank Pat Doherty for all of his assistance. We would like to thank Professor Michael Martin for his assistance with the flow visualization portion of our thesis. We would like to thank Professor Adrian Onis for his help in validating our foil results. We would also like to thank our editor, Professor Harris, and our reader, Professor Boyd, for their help with the written portion of our thesis. We would also like to thank Michael Copy for his small fingers and coding prowess, as well as Burke Kanemasu for his help with the foil analysis program XFLR5. The first wind tunnel was invented in 1871 by Frank Wenham. At this time, model testing was conducted with whirling arms, which spun a model in a large circle. A picture of a whirling arm can be seen above. Wenham was dissatisfied with the results he was getting from these arms and created the first open circuit wind tunnel. His tunnel was 12 feet long and had an 18-inch by 18-inch cross-section. In the early 1900s, the Wright brothers built an open circuit wind tunnel, which was crucial in the development of the world's first airplane. Wind tunnels allow for the collection of experimental data and can be used to measure the lift and drag forces on a test subject. These forces can then be converted into non-dimensional 2D or 3D coefficients. Wind tunnels can also be used to visualize fluid flow over a test subject. Wind tunnels are commonly used for the analysis of airfoils. Airfoils are intended to maximize the lift they create while minimizing their drag. The above graphic is an output from the foil analysis program XFLR5. A NACA 0012 foil was analyzed in this program for illustrative purposes. The x-axis shows the angle of attack of the foil, while the y-axis shows the magnitude of the lift and drag coefficients. As the angle of attack of a foil changes, so do the lift and drag forces acting on it. As the angle of attack increases, we expect to see an increase in lift, with a relatively small increase in drag. This trend will continue until the angle of attack increases so much that the foil stalls and loses lift quickly. At the same angle that we expect to stall, we expect to see a sharp increase in the foil drag. This creates a region known as the drag bucket, where the foil drag is relatively constant with respect to its change in lift. Lift and drag coefficients allow for the application of wind tunnel testing to full-scale items. These coefficients can be 2 or 3-dimensional. 2D coefficients exclude end effects and wingtip losses and are applicable to strip theory. The above formula consists of the lift or drag forces in the numerator, while in the denominator, rho represents the fluid density, u represents the free stream velocity, and c represents the model chord. These 2D coefficients are in terms of lift or drag per unit span. 3D lift coefficients include end effects and allow for the non-dimensional analysis of foils that have non-uniform sections. The 3D formulation is much the same as the 2D. However, where the 2D formulation uses the model chord, the 3D coefficients use the projected area of the foil, which is the product of the mean chord and the mean span. The Reynolds number is a non-dimensional value that is useful for establishing dynamic similarity between a scale model and a full-sized object. The Reynolds number is a ratio of the inertial to viscous forces on a test subject as it moves through a fluid. By matching the Reynolds number of a scale model to that of a full-sized object, the forces acting on that full-size object can be accurately predicted. The Reynolds number formulation can be seen above, where U represents the free stream velocity, X is the characteristic length, and nu is the kinematic viscosity. Wind tunnels can be classified in two main ways. The first of these is the intake system. Open circuit wind tunnels are open on either end and continually cycle fresh air through the test section. In a closed loop tunnel, the same fluid is recirculated through the test section throughout the duration of the test. The figure above shows NASA's closed loop wind tunnels. Wind tunnels are also classified based on the maximum wind speed achieved in their test section. These classifications are based on Mach number, or the ratio of the fluid speed to the speed of sound through that fluid. Subsonic tunnels operate below the speed of sound and below Mach numbers of 0.8. Transonic tunnels operate between Mach numbers of 0.8 and 1.2. Finally, supersonic tunnels operate at speeds exceeding the speed of sound and fall between Mach numbers of 1.2 and 5. The Webb Institute wind tunnel is an open circuit subsonic tunnel. The figure above shows a CAD diagram of our wind tunnel. The Webb tunnel has a maximum test section speed of 38 miles an hour and is equipped with a 2-axis air-bearing rig. Our wind tunnel was originally built in 2012 by New England Boat Works for Navitec and was operated in Rhode Island. Navitec was funded by the Office of Naval Research and stated that the wind tunnel was to be donated to Webb when Navitec finished using it. The tunnel was donated to Webb in 2017 when its initial setup began. In his 2020 thesis, Alec Gonzalez worked to set up the wind tunnel. However, his work was curtailed due to the COVID-19 pandemic. At the start of our thesis, the wind tunnel could be powered on manually. However, all data collection systems and the wind tunnel computer control interface were neither installed nor functional. The objectives of our thesis were to commission the Webb Institute wind tunnel, calibrate its test section flow characteristics, and validate the tunnel results. To outline our presentation, I will discuss the procedure we use to accomplish our objectives, as well as the repairs and setup of the Webb wind tunnel. Eli will then discuss the validation, testing, and results in conclusion of our thesis before concluding with recommendations for future work. To accomplish our objectives, we set up the testing rig, we debugged and repaired the wind tunnel control program, we calibrated the tunnel instruments, we established a test section velocity profile, we validated tunnel data against known results, and we installed flow visualization equipment. The repairs and setup of the wind tunnel began with the installation of seam compound. The tunnel is fit with a series of removable screens to straighten the airflow into the test section. Seam compound was used to fill the gaps around these screens. Next, the flow visualization equipment was installed. Flow visualization allows for the operator to see airflow over a test subject and is useful for the qualitative analysis of separation and vorticity. Flow visualization is achieved by burning oil on a wire, which creates trails of smoke through the test section. A DC power supply was installed to power this wire. Stage lights were also hung beneath the test section to illuminate the foil. As shown by the photo above, the newly installed flow visualization equipment is up and running. Smoke trails clearly show the path of airflow through the tunnel. These trails can be clearly seen by eye and are easily captured with a basic camera. Above is a NACA 0012 foil at a 7-degree angle of attack. This figure shows the same foil at a 15-degree angle of attack. Once again, the airflow around the foil can be clearly seen. If we look at these two photos together, we can clearly see expected airfoil theory. In the 7-degree condition, the airflow remains attached to the foil, while in the 15-degree condition, the foil has stalled. A clear separation region can be seen in the flow visualization. Next, the 2-axis air-bearing rig was installed on top of the tunnel. This rig is supported by an 80-20 frame and allows for the mounting of foils in the test section. Atop the rig is a stepper motor, which can rotate and control the angle of attack of the foil in the test section. The rig can translate with the flow as well as orthogonally to it. Load cells are positioned on each of these axes to measure lift and drag forces produced by the foil. Friction is eliminated from these translations with the use of air bearings, which operate at 60 psi. These air bearings are connected to the Haverly Lab compressor and fed through a dryer and regulator. Next, the pitot tube was installed in the wind tunnel. This is used for the measurement of the wind speed through the test section. The pitot tube passages were cleaned with vinegar prior to its installation. All of the wind tunnel instruments are wired to one central electronics board. The wind tunnel is equipped with a module to control the stepper motor, a module to process the load cell signals, a differential pressure sensor and processor for the pitot tube measurements, and a temperature and humidity sensor. The electronics board's processors all feed into a LabVIEW computer interface. A screenshot of this interface during testing can be seen above. This virtual instrument, or VI, allows for control and data collection from the tunnel, and this main VI is supported by hundreds of smaller sub-VIs. The wind tunnel LabVIEW interface allows for the user to input foil parameters and a testing matrix. The tunnel then measures lift and drag forces at the desired speeds and angles of attack. The fluid properties, as well as the foil parameters, are then used to calculate non-dimensional lift coefficients, and these are plotted against angle of attack in real time. The wind tunnel software had many errors at the start of our thesis and was incapable of running. The first error was the product of a missing dynamic link library, or DLL. This DLL was found online and installed within the wind tunnel program. The wind tunnel was last set up using LabVIEW 2016, so we upgraded it to LabVIEW 2024. LabVIEW 2016 had an internal calculation program called MathScript that is not supported by LabVIEW 2024. As such, all calculation scripts were migrated to MATLAB. The code was also riddled with file path errors, where the software was looking in incorrect folders for relevant files. All of these were resolved. Finally, the calibration script, a separate VI, was updated to use MATLAB. It was also modified to save a running history of calibration files so users can recall old calibrations if desired. Despite the resolution of the MathScript and file path errors, the pitot tube was still throwing an error and was incapable of communicating wind speeds. It was determined that the source of the error was the National Instruments signal processing module connected to the pitot tube. The tube was wired to an analog input, or AI module. This is designed to take inputs from a computer and convert them into a voltage to control physical components. However, because the pitot tube differential pressure sensor produces an output voltage, an input module is incapable of communicating with it. This AI module was replaced with an analog output, or AO module, which takes the voltage from the pressure sensor and converts it into a signal that the LabVIEW software can interpret. The resolution of this error had the wind tunnel up and running. I will now pass the presentation off to my thesis partner, Eli Murray.
Thank you, Thomas. Once the wind tunnel was fixed to a point where it could consistently run the program without encountering errors, the validation process began. The wind speed voltage was calibrated by recording the voltage of the signal sent to the wind tunnel motor and recording what wind speed the motor produced. This was repeated at several different speeds, and the results were plotted with a line of best fit. The motor controller was then given the equation of this line of best fit, allowing the motor to be calibrated appropriately. The R-squared value being so close to 1 shows a very strong linear trend between input and output. After the motor controller was adjusted, a velocity profile of the wind tunnel was created. The Webb wind tunnel velocity profile can be seen on the left. This profile was made by moving the pitot tube in 4-inch increments and recording the wind speed at each point. Navitek conducted a similar velocity profile test when they had the wind tunnel, and it can be seen on the right. As you can see, the velocity profiles are very similar. This velocity profile can be used to determine an appropriate placement of the pitot tube, where it is out of the way while still remaining in the flow. Next, the load cells were calibrated to ensure a linear relationship between load input and load output. This is done using a VI named AutoCal. Known weights are applied to the load cells and the output is measured. The data is graphed and a line of best fit is created. This data was then saved to a calibration file, which is read by the main program automatically. The R-squared on these graphs is typically 0.9999, again showing a strong linear relationship between input and output. Finally, the stepper motor that controls the angle of attack of the foil needed to be taired. Tearing the motor ensures that the LabVIEW program knows where 0 angle of attack is for the foil. This is done by squaring the foil to the test section wall and tearing the angle of attack controller in the main VI. This figure above shows the squaring process. To test the accuracy of the data produced by the wind tunnel, we began testing 2 foils, a NACA 0015 and a NACA 0012. The NACA 0015 foil was provided by Navitek, and the 0012 was 3D printed here at Webb. Both foils were tested using the following test matrix. This test matrix tests wind speeds of 2 to 16 meters per second at steps of 2 meters per second. At each wind speed, the foil moves from negative 20 degrees angle of attack to 20 degrees angle of attack in steps of 1 degree. One of the strengths of the wind tunnel main VI is that it can run this entire test in one continuous run without requiring user input between tests. The NACA 0015 foil is short enough to test 3D coefficients. We kept the foil near the top of the test section and used an end plate on that end, with the other end of the foil being open to the flow of fluid in the tunnel. In doing this, we created a symmetry plane for the foil. The concept of the symmetry plane is that when a foil is connected to an infinite flat plate, the lift generated is similar to a foil with twice the aspect ratio and no end plates. The added drag of the end plate we had on our foil was accounted for by adding a parasitic drag factor into the results. The parasitic drag feature is built into the main VI program. To validate the wind tunnel results, the program XFLR5 was used. The NACA 0015 wing was modeled, as can be seen above, and the same test matrix was analyzed. However, XFLR cannot capture end plate effects, which is why we used a symmetry plane. As such, the XFLR5 model used a span that was double that of the foil we tested in our wind tunnel. The graph here shows the post-process results of the test. The x-axis of these graphs is angle of attack, and the y-axis is the value of the lift or drag coefficient. Each line on the graphs represents a different wind speed. By looking at the lift coefficient graph, which is on top, you can see here that the foil is stalling between 11 and 16 degree angle of attacks, depending on the wind speed. Looking at the drag coefficients on bottom, you can see that there's a drag bucket forming at these associated stall angles. These trends are accurate to the established theory and the fact that as wind speed increases, the Reynolds number increases, and the flow takes longer to separate from the foil, corresponding with a higher stall angle at higher wind speeds. You can also see that there is a relatively constant lift slope, and that at very low wind speeds, the lift coefficients remain near zero between -3 and 3 degree angle of attack, which is also accurate to theory. Now, we will focus on the 10 meter per second test to get a closer look at the data. This graph shows the NACA 0015 10 meter per second test compared to XFLR. The XFLR data is shown as dotted lines, and the wind tunnel data is shown as solid lines. Again, the y-axis is the value of the lift or drag coefficients, and the x-axis is the angle of attack. Please note that XFLR cannot compute stall in 3D, which is why the dotted lines do not go past 13 degree angle of attacks. Although the foil in the wind tunnel stalls at a higher angle of attack than what is expected in XFLR, and the wind tunnel data deviates most between 5 and 9 degree angle of attack, it can be seen that the results between XFLR and the wind tunnel are very similar. As mentioned earlier, the NACA 0012 was printed here at Webb. This allowed us to create a foil that spanned the entire test section, which allowed us to negate end effects from the foil, enabling the collection of 2D coefficients. Because we were able to gather 2D coefficients, we could compare our data to XFoil, which is a 2D program and is known to be more accurate than the 3D XFLR. The graph here shows the post-processed results of the test. The trends of this data are accurate with the drag bucket, lift slope, and stall angles. Again, we will focus on the 10 meter per second wind speed test. This graph shows the NACA 0012 10 meter per second test compared to XFoil. The dotted lines are the XFoil, and the solid lines are the test data. As you can see, the XFoil is over-predicting the lift coefficient, but the stall angle and drag bucket are accurate. Furthermore, although the magnitude is less similar, the non-linear lift slope pattern matches between the tunnel and the XFoil data. An interesting trend appears with the foil when it is stalled, where the XFoil predicts a steep drop in lift. As you can see, in reality, the lift coefficient of the tested foil does drop off, but not by very much. Lift coefficients at stall angles of attack are expected to be relatively constant, but the wind tunnel shows a bit of a double step in lift coefficient at stall. In conclusion, the Webb wind tunnel has been commissioned. All provided equipment has been installed and validated, and the program runs without errors. The data produced by the tunnel is accurate and repeatable, allowing researchers to rely on the wind tunnel's results. Finally, a user manual and data post-processing script has been created to aid with future use of the wind tunnel. Our recommendations for future work are as follows. Although the program works well now, it cannot run added mass tests. The main VI could be modified to allow for added mass experiments in the future. Further, the smoke generation side of the flow visualization could be updated to provide more consistent smoke for longer periods of time. However, even without these upgrades, the wind tunnel can currently be used to aid with testing foils, experiments with flaps, and more. Thank you for attending the presentation of our thesis, Webb's Open Circuit Wind Tunnel, Final Setup and Validation. I ask you to please hold questions until the conclusion of Michael and Andrew's thesis presentation.